Emerging Technologies and Designing the Smart University. The topic for this YouTube video is Designing the Smart University, Strategies for Curriculum, Management, and Academic Planning with AI Agents, Quantum and Emerging Technology. The dawn of the smart university. The 21st century marks the beginning of a transformative era in education, where artificial intelligence, AI agents, quantum technologies, and emerging technologies collectively form the cognitive and operational foundation of future universities. The smart university is not merely an institution. It is a living, intelligent ecosystem designed to sense, adapt, learn, and evolve. It represents the merging of human creativity and machine intelligence into a unified framework capable of solving complex problems, designing adaptive learning systems, and managing academic operations with precision and foresight. The transformation driven by these technologies will profoundly redefine how humanity educates, innovates, and governs knowledge systems, creating an entirely new paradigm of intelligent, sustainable, and interconnected education. AI in curriculum design and learning innovation. Artificial intelligence has become the nucleus of modern academic innovation, serving as both an analytical tool and a creative partner in curriculum development. Through data-driven insights, AI systems can continuously assess global trends, industry needs, and learner progress to update course materials and learning pathways dynamically. Deep learning algorithms and natural language processing enable adaptive learning platforms that understand individual cognitive patterns and design personalized educational experiences. AI-driven educational analytics allow institutions to predict student success, identify skill gaps, and align curriculum development with emerging fields such as quantum computing, AI ethics, and sustainable engineering. Intelligent tutoring systems use AI to deliver content interactively, offering contextualized feedback and continuous assessment. These dynamic models enhance inclusivity by supporting diverse learners and by ensuring that education adapts to human potential rather than requiring humans to conform to static educational structures. AI agents in academic management and institutional planning. AI agents extend the boundaries of intelligence within university systems. These autonomous digital entities can collaborate, negotiate, and coordinate within complex academic and administrative ecosystems. In academic management, AI agents perform scheduling, resource optimization, faculty workload balancing, and student advising. Using principles of multi-agent systems in game theory, they can handle competing objectives such as cost efficiency, academic quality, and student satisfaction simultaneously. In governance, AI agents can simulate policy impacts and optimize decision-making using predictive modeling. They can interact with humans and other digital entities through cooperative learning frameworks that ensure strategic equilibrium in decision processes. AI-driven dashboards supported by intelligent agents provide real-time insight into institutional operations, transforming decision-making into an intelligent, evidence-based process. These systems empower administrators to anticipate problems before they arise, plan more efficiently, and maintain institutional resilience in changing environments. Quantum technologies in academic strategy and institutional intelligence. Quantum technologies introduces an entirely new dimension of computational and analytical power to the smart university. Quantum computing enables the simulation and optimization of complex educational systems far beyond the capacity of classical computers. Quantum algorithms can manage multidimensional data to predict long-term educational outcomes, analyze socioeconomic variables, and guide strategic decisions on research investment and infrastructure development. Quantum machine learning integrates with AI systems to process large educational datasets at quantum speed, uncovering correlations that remain hidden within traditional analytics. Quantum communication ensures security and confidentiality through quantum key distribution, providing universities with the highest level of data protection in a world increasingly vulnerable to cyber threats. Quantum-inspired algorithms further enhance resource optimization, logistics management, and sustainability planning within campuses. In research management, quantum computing accelerates discovery processes, from materials science to healthcare innovations, embedding quantum thinking into the intellectual fabric of the smart university. Emerging technologies in the cognitive campus. Beyond AI and quantum, other emerging technologies contribute vital functionalities to the smart university. The Internet of Things, IoT, connects classrooms, laboratories, and administrative offices into a network of intelligent sensors and devices. This digital nervous system continuously monitors energy usage, environmental conditions, and operational efficiency to create a sustainable campus environment. Virtual reality and augmented reality transform the classroom into an immersive learning space where students can conduct experiments, explore distant environments, and interact with digital twins of real-world systems. Blockchain technologies establish immutable ledgers for credential verification, research tracking, and transparent governance. Robotics automates routine operations, assists in laboratories, and supports accessibility for individuals with disabilities. Neuromorphic computing systems simulate brain-like processes for adaptive learning, while 6G communication networks ensure instantaneous global connectivity. Together, these technologies create a cognitive campus, an environment that senses, learns, and responds to the needs of its inhabitants. Integrated paradigm of intelligence and management. The true power of the smart university lies not in isolated technologies but in the integrated paradigm that unites AI agents, quantum, and emerging technologies into one intelligent continuum. This convergence allows universities to manage complexity through hybrid intelligence systems where human expertise collaborates with machine cognition. Data flows seamlessly across domains, research, administration, student services, and strategic planning, creating a holistic understanding of institutional performance. Quantum-enhanced AI models predict economic and social shifts affecting education. AI agents translate those predictions into actionable management strategies, and emerging technologies implement them through autonomous operations. This integrated framework supports self-optimizing decision loops, ethical governance, and sustainable growth. By combining computational speed, learning intelligence, and human creativity, the smart university achieves equilibrium between innovation and responsibility, efficiency and inclusion, progress and ethics. Applications across education, research, and society. The smart university paradigm has widespread applications across all domains of academia and beyond. In education, adaptive AI tutors provide real-time feedback and personalized learning pathways. In research, AI and quantum platforms enable predictive experimentation, accelerating discovery in physics, medicine, and engineering. In business schools, multi-agent AI systems simulate market dynamics and optimize resource allocation. In healthcare faculties, quantum-enhanced analytics aid in drug development and precision medicine. In engineering, digital twins model infrastructure systems for energy efficiency and sustainability. In public policy and governance education, AI-driven models simulate social systems to predict the impact of laws and interventions. These interconnected applications transform the university into a global knowledge hub capable of generating actionable insights for industries, governments, and communities. The smart university becomes both a creator and a connector of knowledge, driving innovation that improves humanity's collective well-being. The profound significance for humanity and global development. The transformation of universities into intelligent, quantum-enabled institutions represents one of the most profound shifts in human civilization. It signifies the evolution of knowledge itself, from static content to dynamic intelligence. By embedding cognition into the structure of universities, humanity acquires the ability to manage learning ecosystems as living systems capable of growth and adaptation. The integration of AI and quantum systems enhances global collaboration, accelerates innovation, and ensures that education remains the core driver of sustainable development. It redefines the role of universities from passive repositories of information to active engines of societal transformation. The smart university will not only educate students but also generate solutions for global challenges such as climate change, health crises, digital inequality, and ethical governance. Technical vision and collaborative invitation building. The smart university requires technical excellence, visionary planning, and interdisciplinary collaboration. Researchers, technologists, educators, and policymakers must co-create the infrastructure, frameworks, and algorithms that will shape this intelligent academic world. Collaboration across domains such as quantum computation, AI engineering, data science, educational psychology, and sustainability design is essential. Each discipline contributes to the collective intelligence that will define future universities. AI architects can design adaptive platforms for learning and management. Quantum scientists can build computational frameworks. Educators can define ethical and pedagogical standards, and administrators can deploy these systems strategically. The mission is global and deeply human, to align technology with education for the advancement of mankind. Those who engage in this collaborative journey will contribute to creating institutions capable of designing the intelligent, sustainable, and equitable world that humanity urgently needs. Conclusion: the Smart University as humanity's next frontier. Designing the smart university with AI agents, quantum, and emerging technologies represents not only a technological advancement but also a new philosophy of education and governance. It aligns intelligence with purpose, efficiency with ethics, and technology with humanity. This integration will empower universities to become self-evolving ecosystems, dynamic, ethical, and intelligent. It will enhance creativity, accelerate innovation, and ensure that education continues to guide civilization towards sustainable progress. The Smart University is humanity's next frontier, a place where artificial and human intelligence unite to illuminate the path of knowledge, wisdom, and global transformation. Researchers, educators, and innovators are invited to collaborate in shaping this magnificent paradigm. Together, we can build the intelligent institutions that will guide the evolution of knowledge and ensure that mankind's greatest power, intelligence, serves its highest goal: a better, wiser, and more harmonious world. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.
The topic for this video is Designing Smart Universities and Education Systems, All Frontier Technologies for the Future of Education and Learning, the Dawn of a New Educational Age. Education is entering an extraordinary era, one defined not by simple digital transformation but by a technological renaissance across every scientific and engineering frontier. The future university is no longer a place defined only by classrooms, lecture halls, or textbooks. It is a living, intelligent ecosystem where artificial intelligence, quantum computing, biotechnology, extended reality, robotics, and sustainable energy systems converge to create learning environments that think, adapt, and evolve with every learner. The smart university of the future will not merely teach knowledge, it will generate, personalize, and apply knowledge through advanced, interconnected technologies that transcend disciplines. This evolution demands a new imagination. It requires that educators, researchers, policymakers, and industry leaders work together to build education systems that are intelligent, inclusive, sustainable, and adaptive to human potential. Let us explore how all frontier technologies are shaping the architecture of future learning. Artificial intelligence and AI agents. The cognitive core of the smart university. At the heart of the smart education ecosystem lies artificial intelligence, not as a tool, but as a collaborator. AI enables a personalized learning experience that adapts to the pace, style, and curiosity of each learner. Intelligent tutoring systems use predictive analytics to identify learning gaps. Natural language models act as conversational mentors available 24/7. But the most transformative evolution is the rise of AI agents, autonomous, adaptive systems that can plan, reason, and collaborate with humans. AI agents manage course scheduling, optimize research funding, assist in academic writing, and even provide mental well-being support. They coordinate learning across platforms, ensuring that each student's experience is uniquely optimized. For teachers and administrators, AI agents simplify decision-making by analyzing massive institutional datasets, creating universities that are not just automated but intelligently orchestrated. Quantum technologies. Accelerating research, learning, and security. The arrival of quantum technologies marks a turning point for research-intensive universities. Quantum computing's power to simulate complex phenomena, from molecular reactions to climate systems, will transform the research curriculum. Students will soon engage with quantum simulators as naturally as they use computers today. Quantum communication and cryptography will redefine how institutions safeguard their data, intellectual property, and student information in the post-quantum era. Beyond computation, quantum sensing technologies will enhance precision in science, medicine, and environmental studies. Together, these advances will give birth to the quantum university, a place where quantum algorithms, AI models, and classical systems cooperate to expand the frontiers of human knowledge. Extended reality. Learning beyond space and time. Augmented reality, AR, virtual reality, VR, and mixed reality, MR, technologies will dissolve the boundaries of traditional learning. Students will conduct laboratory experiments in safe, immersive simulations. History students will walk through reconstructed ancient civilizations. Engineering students will visualize fluid dynamics or quantum waveforms in three-dimensional holographic form. Through these technologies, learning becomes experiential. Universities can reach students anywhere in the world through immersive metaverses, offering global classrooms where interaction, creativity, and collaboration thrive. The extended reality ecosystem will make education more accessible, engaging, and impactful. Robotics and human-robot collaboration. The new academic environment will not only be intelligent, it will be physically interactive. Educational and service robots will assist teachers, guide students, perform repetitive administrative tasks, and maintain campus operations. In laboratories and healthcare faculties, robotic systems will train students to perform complex surgical or engineering tasks with precision and safety. The combination of robotics and AI agents will also play a central role in assistive education, supporting students with disabilities, offering rehabilitation learning through motion-assisted exoskeletons, and creating inclusive participation for all. Smart campuses will evolve into ecosystems where humans and machines collaborate seamlessly to extend human capabilities and creativity. Internet of Things and cyber-physical systems. At the infrastructure level, the Internet of Things, IoT, and cyber-physical systems, CPS, will become the nervous system of smart universities. Every classroom, lab, and device will be connected through intelligent sensors. Energy consumption, air quality, and occupancy will be monitored and adjusted autonomously for sustainability and efficiency. Wearable IoT devices will track learning engagement, concentration, and even student well-being. Data collected from these systems will feed into AI models that continuously improve the campus experience. The smart campus will thus become a living laboratory, an intelligent physical-digital hybrid space where learning and operations merge into a continuous feedback loop. Cloud, edge, and distributed computing for universal access. Future education must be globally accessible. Cloud and edge computing ensure that learning resources, laboratories, and simulations are available anywhere, anytime. Through virtual laboratories hosted in the cloud, students in remote areas can perform high-level computational experiments without specialized hardware. Distributed computing will power open research collaborations, connecting data from universities across the world. Edge computing will enable fast, localized AI responses, improving interactivity in virtual classrooms and research simulations. Together, these systems make knowledge borderless and equitable. Blockchain, Web3, and decentralized learning systems. Education in the future will also require trust, transparency, and mobility, all of which are enabled by blockchain and Web3 technologies. Academic records, degrees, and credentials will be stored securely on distributed ledgers, verifiable globally without intermediaries. Smart contracts will automate research collaboration and intellectual property management. Decentralized learning systems will empower students to own their educational data and seamlessly transfer credentials between universities, employers, and nations. Blockchain will lay the foundation for a global, trusted education economy. Biotechnology, neurotechnology, and human enhancement. The merging of biology and technology will redefine what it means to learn. Neurotechnology and brain-computer interfaces, BCIs, will measure cognitive responses, enabling adaptive learning that synchronizes with brain activity. AI models will detect cognitive fatigue and dynamically adjust the pace of teaching. Biotechnology and health monitoring devices will personalize learning based on physiological and emotional states. In health, sports, and psychology programs, biotechnology will enable deep insight into human performance and cognitive development. Education will no longer be confined to information absorption, it will become a biologically attuned experience. Sustainable technologies and smart energy systems. A true smart university must also be a sustainable university. Advanced materials, renewable energy systems, and green campus technologies will create carbon-neutral learning environments. Buildings will harvest solar energy, store it in smart grids, and use AI to optimize energy flows. Students will study sustainability not only as a subject but as a lived experience, learning from real-time energy dashboards and environmental monitoring systems. The campus will become a microcosm of global sustainability practice, demonstrating how frontier technologies can lead both educational and environmental transformation. Data science, digital twins, and institutional intelligence. Every aspect of future education will depend on data-driven decision-making. Universities will build digital twins, virtual replicas of campuses, operations, and even student experiences. These models will simulate resource use, predict maintenance needs, and optimize strategic planning. AI analytics will monitor academic trends, student engagement, and research impact. This will allow administrators to make proactive decisions grounded in real evidence. The digital twin university is not just efficient, it is self-aware, continuously learning from its own data to improve teaching, research, and governance. AI-augmented programming. A defining feature of the future education ecosystem is democratization of innovation. Low-code and no-code platforms will allow students, educators, and administrators, even without programming skills, to design apps, dashboards, and analytical tools. AI-augmented programming platforms will help staff develop custom solutions rapidly, empowering every department to innovate independently. This will transform universities from being technology consumers to technology creators, accelerating innovation and entrepreneurial culture across campuses. The integrated future. Education 5.0 and University 5.0. All these technologies converge towards one paradigm: Education 5.0 and University 5.0, an era of intelligent, inclusive, and sustainable learning ecosystems that integrate human intelligence, artificial intelligence, quantum intelligence, and biological intelligence. Education 5.0 envisions universities as continuously evolving systems, connected to industries, communities, and global networks. Learning will be lifelong, adaptive, and co-created with technology. Professors will work with AI agents, digital twins, and global learners in hybrid physical-digital classrooms. Knowledge will be generated through collaboration between humans and machines, science and art, data and creativity. Conclusion. The future is now. Designing smart universities and education systems is not a distant aspiration, it is today's responsibility. The fusion of frontier technologies has given us an unparalleled opportunity to redefine education for the 21st century and beyond. The future university will not be limited by geography, language, or technology. It will be intelligent, empathetic, sustainable, and human-centered, an ecosystem where every student learns not only to use technology but to think with it, innovate through it, and shape the world using it. Let us build this future. A world where education becomes the most intelligent system on Earth, designed by all frontier technologies for all humanity. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.
The video topic is all key emerging technologies shaping future education systems, universities, TAFES, and colleges. This video provides a comprehensive synthesis identifying all key technologies shaping future education systems, universities, TAFEs, and colleges. The list is grouped by domain, and these technologies go far beyond computing or IT technologies. Artificial intelligence and AI agents. AI and its agentic forms are the foundation of future education systems. Key impacts: personalized learning. Adaptive AI tutors and intelligent feedback systems create tailored learning pathways for each student. AI agents for academic planning and governance. Multi-agent systems optimize enrollments, staff workloads, and curriculum design. Assessment and evaluation. AI-driven analytics measure learning outcomes in real time. Administration. AI automates admissions, finance, compliance, and timetabling. Research support. AI copilots assist in literature reviews, simulation, and grant writing. Quantum technologies. Quantum computing and quantum communication will reshape research, simulation, and security in universities. Key impacts: quantum simulation enables complex scientific experiments, materials discovery, and climate modeling within the classroom or lab. Quantum cryptography protects university data and research against post-quantum cybersecurity threats. Quantum AI integration merges quantum algorithms with machine learning for next-generation educational tools. Quantum education ecosystems, new curricula and degrees in quantum information science, engineering, and applications. Extended reality, XR, technologies, AR, VR, and Mr. Immersive learning will redefine how knowledge is delivered and experienced. Key impacts: virtual laboratories. Students can perform chemistry, physics, or engineering experiments safely in digital environments. Mixed reality classrooms blend real and virtual spaces for interactive simulations and collaboration. Cultural and field experiences. Archaeology, geography, and design students explore virtual field sites or heritage locations. Robotics and human-robot collaboration. Robotics and mechatronics are transforming learning, assistance, and campus management. Key impacts: teaching and learning. Robots assist teachers, demonstrate engineering concepts, or support special needs students. Service robots manage logistics, cleaning, and safety on smart campuses. Rehabilitation and biomechatronic systems used in health and sports science education. AI-controlled exoskeletons for biomedical and biomechanical training and research. Internet of Things, IoT, and cyber-physical systems, CPS, smart, connected infrastructure forms the digital nervous system of future campuses. Key impacts: smart classrooms, automated lighting, energy, and environment control. Wearable learning devices track engagement, focus, and wellness. Research data collection, real-time sensors for environmental and engineering studies. Smart campus operations, integrated building, transport, and safety systems. Cloud, edge, and distributed computing. These technologies provide computational power and access for global learners. Key impacts: edge learning platforms, low-latency AI inference near learners. Cloud laboratories, remote access to high-performance computing and experiments. Data lakes for universities, centralized research and academic data for AI and analytics. Blockchain and Web3 technologies. They enable trust, transparency, and mobility in academic and research records. Key impacts: blockchain credentials, secure, verifiable degrees and certificates. Smart contracts for collaboration, automate research agreements and IP management. Decentralized learning systems, students own and share their educational data globally. Biotechnology, neurotechnology, and brain-computer interfaces, BCIs. These frontier fields will reshape human learning capacity itself. Key impacts: cognitive enhancement, neuroadaptive systems that detect fatigue and optimize learning pace. Brain-computer interfaces enable new ways of interaction and accessibility for all learners. Health and biomedical curricula Integration of biotech and AI in life sciences education. Advanced materials and sustainable energy technologies. The university campus will become a living sustainability laboratory. Key impacts. Green buildings. Materials with self-healing, energy harvesting, or carbon-absorbing capabilities. Renewable energy systems. Solar, hydrogen, and energy storage technologies embedded in teaching and operations. Sustainability education. Real-time environmental data integrated into curricula. Data science, analytics, and digital twins. Digital twins of campuses, laboratories, or even entire universities will support strategic decision-making and experimentation. Key impacts. Student digital twins. Predict dropout risks, performance trends, and well-being needs. Campus digital twins. Optimize energy, maintenance, and traffic flow. Institutional analytics. Drive data-driven strategic planning. DDITIVE manufacturing, 3D, 4D printing, and advanced manufacturing transforming engineering and design education. Key impacts. Prototyping labs. Hands-on innovation and design thinking. 4D printing. Smart materials that change shape or function over time. Curricular integration. Teaching sustainability and creativity through fabrication. Cybersecurity and post-quantum security systems protecting intellectual property, digital campuses, and research networks. Key impacts. Quantum-resistant cryptography. Safeguards academic databases. Cyber-resilient campuses. Autonomous defense systems using AI. AI-augmented programming. These democratize innovation across disciplines. Key impacts. Educators and students as developers build custom tools, dashboards, or micro-apps without coding expertise. Accelerated research tools. Automate data processing and experimentation. Cross-disciplinary collaboration. Business, science, and engineering departments co-develop digital solutions. Generative AI and creative technologies transforming content creation, assessment, and communication. Key impacts. Automatic learning material generation. AI creates tutorials, quizzes, or simulations. Creative county design. AI assists in architecture, media, and design disciplines. AI-enhanced research writing. Accelerates publication and collaboration. Socio-technical and ethical AI systems. Universities must integrate responsible innovation. Key impacts. AI ethics education. New curricula in responsible AI and technology governance. AI governance systems ensure fairness, transparency, and inclusiveness. Human-centered design. Keep technology aligned with educational values. The integrative vision. All these technologies together form the technological ecosystem of the smart university. They create adaptive, intelligent, and sustainable learning environments, blending human wisdom with digital intelligence to enhance learning quality, expand access, reduce administrative burden, and accelerate research, innovation, and societal contribution. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity. Title: Quantum Technologies in Computing: Transforming University Administration Strategies, Curriculum Development, and Academic and Research Planning. A short video. You can contact Professor Sardar Mn Islam or Naz for questions and comments at the following email address: sardar.islam@vu.edu. Quantum. The dawn of a new scientific civilization. The rise of quantum technologies is not merely a scientific breakthrough. It is a monumental leap in human evolution. As profound as the invention of the wheel, electricity, or the internet, quantum is poised to transform the world, mankind, and even the universe itself. Designated by the United Nations as the 2025 International Year of Quantum Science and Technology, this milestone signals an urgent global recognition. Quantum is the next defining frontier of knowledge, power, and progress. Whether it's curing diseases, solving climate change, transforming computing, or unlocking the mysteries of the cosmos, quantum technologies promise to redefine what is possible, bringing the invisible forces of quantum physics into real-world applications that will touch every life, industry, and nation. The quantum imperative for universities: lead or be left behind. Universities are at a strategic crossroads. Quantum computing, quantum sensing, quantum communications. These are no longer experimental fields tucked away in labs. They are core drivers of the next profound global technological transformation, rapidly reshaping government strategies, industry priorities, and scientific research. Higher education institutions must act now. If universities fail to proactively embrace and integrate quantum technologies, they risk irrelevance. Those that lead will thrive as centers of innovation, funding, and talent. Those that lag will be excluded from the future economy, global rankings, and meaningful research partnerships. Quantum as a catalyst for institutional transformation. 1. University administration strategies must evolve. Quantum is not an elective, it is a strategic mandate. University leadership must establish quantum strategy offices or vice presidential roles. Embed quantum futures in strategic planning and governance. Form partnerships with quantum tech companies and research alliances. This is not just about technology adoption, it is about reimagining the university as a forward-thinking institution that shapes, rather than reacts to, global transformations. 2. Curriculum development. From classical to quantum literacy, today's students must be tomorrow's quantum literate citizens. This means introducing interdisciplinary quantum courses across all faculties, not just physics or computer science, but business, law, ethics, and policy. Creating quantum minors, certificates, and dual degrees. Investing in simulation tools, labs, and partnerships with cloud-based quantum platforms, e.g., IBM Q, D-Wave. Universities must prepare graduates for quantum careers, industries, and challenges that haven't even been imagined yet. 3. Academic and research planning. Quantum-ready institutions' academic planning must move beyond logistics and become future-oriented and quantum-aligned. Use foresight tools to anticipate emerging quantum trends. Prototype new degree programs and credential frameworks. Fund faculty sabbaticals in quantum centers and build collaborative teaching modules with industry experts. Quantum computing will enable unimaginable breakthroughs across fields, from curing diseases to modeling climate, from decoding the brain to unlocking new economic systems. Quantum plus AI. A combined disruption demanding coordinated action. The convergence of quantum computing and artificial intelligence represents a singularity in innovation. This fusion redefines the limits of computation, accelerates scientific discovery and automation, enables transformative change in university operations, from academic advising to institutional planning. Universities must build integrated strategies that align quantum initiatives with AI-driven infrastructure, ensuring ethical, responsible, and effective adoption. The world is moving. Will your university move with it? Leading universities in the world are already Launching quantum innovation hubs. Winning global funding. Reshaping curricula. Attracting top researchers and students. This is a narrow and closing window. Universities that hesitate will be left behind, in prestige, funding, and influence. A final call to visionary leadership. Quantum transformation is not optional, it is existential. For university leaders, this is a once-in-a-century opportunity to reshape their institutions and the future of education, research, and human civilization. The question is no longer whether quantum will change the world, but who will lead that change. Let it be your institution. Let it begin now. Title: Quantum Technologies in Computing, Transforming University Administration Strategies, Curriculum Development, and Academic and Research Planning. Please contact Professor Sardar Mn Islam Naz for comments and questions on the following email address: sardar.islam@vu.edu.au. Part 1. The Strategic Imperative for Higher Education. An Introduction. Quantum is the most significant invention by humans. The United Nations has designated 2025 as the International Year of Quantum Science and Technology. The emergence of quantum technologies marks one of the most consequential turning points in human advancement since the industrial and digital transformation. This new era promises to redefine the limits of what is computationally and scientifically possible, unlocking transformative potential across industries from healthcare and energy to finance, defense, and beyond. At the heart of this disruption lies the power to model, simulate, and optimize complex systems with speed and precision beyond the reach of classical computers. For society at large, this heralds breakthroughs in medicine, climate solutions, cryptography, and artificial intelligence. For universities, however, the implications are even more profound. They are not only expected to understand, adapt, and educate for this quantum future, but also to lead it. As quantum technologies rapidly transition from theoretical constructs to applied systems, higher education must respond with urgency, vision, and strategic action. This video calls upon university administrators, faculty leaders, and academic planners to recognize this unprecedented moment and take bold steps to align institutional strategies with the most powerful technological force of the 21st century. A strategic inflection point for higher education leadership. The global higher education sector is currently encountering a profound technological and intellectual shift that demands urgent and strategic attention at the highest levels of university leadership. Quantum technologies in computing, once confined to theoretical physics and highly specialized laboratories, have now emerged as critical instruments with the potential to fundamentally alter the structures, systems, and priorities of universities worldwide. Their anticipated influence is not speculative, it is immediate and rapidly expanding. Consequently, university administrators must not only become cognizant of these developments but must also take a proactive and leadership-oriented role in integrating them into institutional strategy, academic frameworks, and research agendas. The objective of this communication is to articulate, in unequivocal terms, why and how university administration strategies, curriculum development, academic planning, and research priorities must now be re-evaluated and redesigned to ensure institutional relevance and competitiveness in a quantum-empowered future. The continued viability of universities as centers of excellence, innovation, and societal contribution depends on their ability to anticipate and respond decisively to this emerging technological paradigm. Quantum technologies in computing. A foundational shift in the knowledge economy and the university ecosystem. Quantum technologies refer to a class of innovations based on the principles of quantum mechanics, specifically superposition, entanglement, and tunneling, which enable capabilities far beyond those of classical systems. Quantum computing, in particular, represents a transformative departure from traditional binary computing, offering exponential increases in processing power and problem-solving efficiency in areas such as cryptography, material discovery, logistics, financial modeling, and artificial intelligence. It is imperative to underscore that the global race toward quantum supremacy is already well underway. National governments, multinational corporations, and forward-looking research institutions are investing aggressively in quantum capability development. This momentum will inevitably reshape the knowledge economy. Universities that do not position themselves within this emergent ecosystem risk not only intellectual and technological irrelevance but also a significant decline in research funding competitiveness, industry collaboration opportunities, and global student recruitment. Transforming university administration strategies, a leadership imperative. From a governance and strategic planning perspective, university administrators must urgently reassess existing institutional strategies in light of the disruptive trajectory of quantum technologies. Traditional strategic models, often based on incremental change and historically linear developments, are wholly inadequate in responding to the exponential pace and systemic implications of quantum advancements. University leadership must now frame quantum technology not as a niche research topic but as a comprehensive strategic domain. This requires the establishment of university-wide quantum innovation agendas, the appointment of senior leadership roles dedicated to quantum futures, e.g., Vice President for Quantum Strategy or Director of Emerging Technologies, and the integration of quantum literacy into executive decision-making processes. Furthermore, strategic alliances with government agencies, quantum technology firms, and international research consortia must be proactively pursued to secure institutional positioning in this highly competitive and fast-evolving landscape. Curriculum development. Preparing graduates for quantum futures. The transformation of the academic curriculum is both a responsibility and an opportunity. The current educational models in most universities remain grounded in classical scientific and computational paradigms, thereby failing to equip students with the conceptual frameworks, technical skills, and interdisciplinary awareness necessary for success in a quantum-driven world. A complete and immediate re-evaluation of curricular content is required. Introductory and advanced quantum technology courses must be developed across a broad array of disciplines, not only within physics and computer science, but also within engineering, business, law, ethics, and public policy. Interdisciplinary minors and certificate programs should be introduced, offering students from diverse academic backgrounds exposure to quantum computing principles and applications. In addition, investment in quantum laboratories, simulation tools, and cloud-based quantum computing platforms must be prioritized to support experiential and research-based learning. Moreover, the academic staff must be supported through comprehensive professional development initiatives designed to build capacity in quantum literacy and pedagogy. Faculty training programs, research sabbaticals in quantum centers, and collaborative teaching modules with industry experts must become integral components of the institutional teaching and learning strategy. Academic planning. Aligning institutional frameworks with quantum realities. The responsibilities of academic planning offices must now be fundamentally redefined. In the quantum era, academic planning can no longer operate solely as a logistical function focused on course scheduling and enrollment forecasting. Instead, it must evolve into a forward-looking, integrative function that enables long-term academic coherence, responsiveness to technological trends, and alignment with global workforce needs. Academic planners must incorporate horizon scanning methodologies, scenario planning, and technology foresight into their routine operations. Strategic academic development must be shaped by data-driven insights into the emergence of quantum technologies and their implications for disciplinary evolution, degree relevance, and credential innovation. Planning mechanisms should be calibrated to support the rapid prototyping and deployment of new quantum-focused academic offerings while also ensuring compliance with quality assurance, accreditation, and international benchmarking standards. Research planning. Institutional readiness for quantum-driven discovery. Research planning is a domain where the impact of quantum technologies will be particularly profound. Quantum computing offers capabilities that will transform the methodologies and timelines associated with scientific discovery, simulation, and optimization. Research questions that are currently intractable due to computational constraints will become solvable. This evolution will shift the frontiers of research across fields such as chemistry, biology, medicine, climate science, economics, and social systems. University research offices must begin by conducting institutional audits to assess their current capabilities and readiness to engage in quantum-enhanced research. Strategic investment in quantum research infrastructure, both physical and digital, is required. Moreover, research support frameworks must be adapted to enable interdisciplinary teams to pursue ambitious, high-risk projects in quantum fields. Universities must aggressively pursue funding opportunities associated with national and international quantum research programs. This includes building grant writing expertise focused on quantum priorities, fostering early-stage researcher engagement in quantum projects, and establishing internal seed funding schemes to catalyze institutional innovation. Research partnerships with industry, particularly those engaged in quantum computing, quantum sensing, and quantum communications, must be formalized to enhance translational potential and generate real-world impact. Quantum and artificial intelligence, a combined disruption requiring coordinated response. The convergence of quantum computing and artificial intelligence introduces a level of computational capability that exceeds even the most advanced current systems. This convergence will redefine the scope and speed of data processing, pattern recognition, and automated reasoning. The administrative, pedagogical, and research implications of quantum AI are vast and multifaceted. University leadership must respond by initiating integrated frameworks that link quantum strategy with existing institutional AI policies and infrastructures. Opportunities for using quantum AI in institutional analytics, personalized learning environments, administrative automation, and strategic modeling must be systematically explored. Importantly, ethical frameworks and governance models must be concurrently developed to ensure responsible innovation and safeguard against unintended consequences. Global benchmarking and competitive positioning. A review of international trends reveals that leading institutions are already incorporating quantum technologies into institutional strategy, curriculum design, and research priorities. These institutions are setting global standards, influencing national science and innovation policies, and capturing significant funding and talent. Universities that aspire to global excellence must position themselves within this emerging elite. The window for competitive entry is narrow and closing rapidly. Institutions that delay engagement with quantum technologies will face long-term consequences in reputation, rankings, and relevance. A call to institutional responsibility and strategic leadership. The quantum era is not a distant possibility. It is an immediate and transformative reality. For universities, the implications are comprehensive and unavoidable. Leadership must act with urgency, clarity, and conviction. Strategic frameworks must be revised. Curricula must be modernized. Academic and research planning processes must be re-engineered. The role of the university, as both a generator and disseminator of knowledge, is at stake. University administrators have a unique responsibility, not only to safeguard the future of their institutions but to shape the future of education, innovation, and society. The question is not whether universities will be affected by quantum technologies and computing, but whether they will lead or lag behind. The answer must be found in decisive, informed, and visionary action, starting now. Part 2. Strategic frameworks and institutional pathways for quantum integration. From awareness to action. Institutionalizing the quantum response. In continuation of our urgent call to integrate quantum technologies into the core operations of universities, this second part focuses on concrete institutional responses. Awareness alone is insufficient. What is now needed is a systematic, high-level integration of quantum imperatives into university governance, planning, operations, and culture. The complexity and magnitude of this technological evolution demand that institutions adopt a structured, yet agile approach to planning and implementation. Universities must treat quantum transformation not as an isolated initiative, but as a whole-of-institution strategic shift, one that requires executive sponsorship, cross-functional coordination, sustained investment, and continuous capacity building. The transformation must be deliberate, phased, and measurable, ensuring long-term impact while allowing flexibility for rapid advancements and unpredictable breakthroughs in quantum research and commercialization. Establishing a university-wide quantum strategic framework. The first and most essential step is the formal development and adoption of a university quantum strategic framework. This framework should be endorsed at the highest levels of governance, by the University Council, Senate, and Executive, and should articulate a long-term vision, specific strategic objectives, and clear implementation pathways for engaging with quantum technologies. Such a framework must address several core domains: leadership and governance, identify executive champions responsible for quantum strategy, establish steering committees or task forces; curriculum and teaching, define goals for quantum integration across faculties, plan phased curriculum rollouts, identify priority disciplines; research and innovation, align research investments and faculty recruitment with quantum opportunities, develop interdisciplinary research themes; infrastructure and capabilities, evaluate and enhance computing, laboratory, and cloud-based resources necessary to support quantum learning and experimentation; external engagement, build international and industry partnerships, pursue competitive grants, contribute to national quantum policy development. Critically, this framework must be dynamic and iterative. It should be updated annually in response to technological advances, funding landscapes, institutional capacity, and global benchmarking. Governance models for quantum integration. To ensure sustained attention and accountability, universities should consider the establishment of a dedicated office for quantum futures or similar institutional entity. This office would operate across academic, research, and administrative domains, coordinating quantum initiatives while reporting directly to senior leadership. Key functions of such an office would include strategic planning and policy alignment, stakeholder coordination across faculties and support units, horizon scanning and external intelligence gathering, capability audits and workforce planning, project management of pilot and flagship programs. Such governance models not only accelerate implementation but also demonstrate institutional seriousness to external stakeholders, including funding bodies, industry partners, and prospective students. Curricular implementation. From concept to classroom, a phased and structured approach is required to integrate quantum content into academic programs. The following model may guide universities in their efforts. Phase 1. Foundation and Awareness, Year 1 to 2. Develop general education modules on quantum technologies in society for inclusion in core undergraduate curricula. Offer faculty-wide lectures and seminars to build institutional awareness. Embed introductory quantum computing concepts into select computer science, physics, and engineering courses. Phase 2. Specialization and Certification, Year 2 to 4. Launch interdisciplinary minors and certification programs in quantum computing, quantum algorithms, and quantum ethics. Support faculty collaboration in the co-development of quantum-focused case studies for use in law, business, and policy education. Introduce project-based courses leveraging IBM Q, D-Wave, or other cloud-based quantum simulators. Phase 3. Institutional Leadership, Year 4 onwards. Establish full degree programs, BSc, MSc, PhD, in quantum science and technology. Create dual degree pathways combining quantum specialization with business, governance, or education. Design capstone experiences and internships with leading quantum technology partners. All stages must be supported by continuous professional development for faculty, including workshops, certifications, and collaborative teaching models with visiting quantum experts. Research infrastructure and talent strategy. Quantum transformation at the research level requires significant attention to infrastructure planning, talent development, and interdisciplinary coordination. Infrastructure planning. Upgrade institutional computing infrastructure to support hybrid quantum classical workflows. Invest in quantum simulation environments and partnerships with cloud-based providers. Develop lab spaces for quantum sensing, communications, and materials experimentation. Talent recruitment and retention. Prioritize the recruitment of faculty with dual expertise in quantum science and pedagogy. Create postdoctoral fellowships and visiting scholar programs focused on quantum applications. Fund early career research grants and quantum innovation seed funds to build internal capability. Interdisciplinary collaboration. Develop cross-faculty research clusters focused on grand challenge problems, e.g., quantum computing for climate modeling, quantum cryptography for national security. Support joint PhD programs and multi-investigator grants. Foster collaborative research cultures through retreats, sandpits, and ideation workshops. Institutional research strategy and quantum alignment. University research strategies must explicitly identify quantum technology as a core priority. Quantum should be reflected not merely in departmental research plans, but in institutional research goals, KPIs, and funding strategies. Key actions include mapping quantum-relevant expertise and facilities across the institution, aligning internal funding schemes with external quantum research calls, developing longitudinal KPIs for measuring quantum research impact, e.g., publications, patents, funding volume, partnerships. Participating in regional and national research initiatives that shape quantum policy, infrastructure, and talent pipelines. Where possible, universities should take leadership roles in consortium bids and multidisciplinary centers of excellence in quantum science and engineering. Administrative transformation through quantum AI synergies. Quantum computing will accelerate the potential of artificial intelligence and data analytics, opening up new possibilities for administrative transformation. Universities must begin planning for the integration of quantum AI into decision support systems, institutional planning models, and administrative operations. Applications may include strategic resource optimization using quantum-enhanced modeling, advanced student progression analytics and risk forecasting, quantum-assisted cybersecurity and data protection frameworks, quantum natural language processing for automated academic advising and course matching. Institutional CIOs, strategy offices, and planning departments must collaborate to identify high-value administrative functions that could benefit from early-stage experimentation with quantum AI hybrids. Financial and risk planning for quantum adoption. Adopting quantum technologies and building institutional capacity requires both significant investment and thoughtful risk management. Universities must incorporate quantum priorities into financial planning and risk assessments. Recommended steps include developing multi-year financial forecasts for quantum investments across infrastructure, curriculum, and research, creating quantum-specific budget lines and establishing endowments or capital campaigns to support long-term growth, identifying technological, reputational, and operational risks associated with quantum initiatives and implementing appropriate mitigation strategies, ensuring that procurement, compliance, and data governance frameworks are updated to reflect quantum-era considerations. Engagement with governing boards and external audit bodies will be critical in justifying and sustaining financial support for these transformative initiatives. Building external partnerships and ecosystem influence. No university can undertake quantum transformation in isolation. Strategic engagement with industry, government, and international academic partners is essential. Actions should include joining national quantum hubs, alliances, or innovation networks, establishing formal MOS with quantum hardware and software companies, partnering with ministries of education, defense, and innovation on talent development and strategic foresight, participating in global quantum summits and thought leadership platforms to amplify institutional influence. Such partnerships not only provide access to expertise and resources but also position the university as a national or regional leader in shaping the quantum future. Final call: from institutional readiness to institutional leadership. Quantum technologies are not a transient trend. They represent a foundational transformation of science, technology, education, and society. For universities, the obligation is clear. Institutions must not only prepare to operate within this new paradigm but must assert leadership in shaping its trajectory. This requires courage, coordination, and vision. University administrators must mobilize the full capacity of their institutions to act. The actions taken in the next 2 to 5 years will define not only the standing of individual universities but also the nature of the global academic landscape. The future of higher education lies not in adaptation alone, but in strategic leadership. Quantum transformation will reward those who act decisively, and it will marginalize those who hesitate. It is not enough to acknowledge the quantum era. Universities must build it. Deliberately, boldly, and now. Thanks for watching and see you in the next video. Please subscribe to the channel for your success.
This video offers an insightful analysis of the most critical emerging technologies and explores their implications for the evolving role of vice chancellors as strategic leaders in a technology-driven era. The vice chancellor is a strategic leader in the age of emerging technologies. The role of the vice chancellor or president in universities such as Victoria University is entering a new phase of global significance. The accelerating development of emerging technologies, artificial intelligence, AI agents, quantum technologies, robotics, and advanced digital systems, appears to be reshaping not only industries but also the very foundations of higher education systems and university management. In this context, the vice chancellor's role may increasingly be viewed not as a direct implementer of technology, but as a strategic leader who interprets, guides, and orchestrates institutional transformation. This transformation seems to extend across governance, academic systems, research directions, and institutional positioning. It presents an opportunity for vice chancellors to shape the future trajectory of their universities by recognizing emerging patterns, framing strategic responses, and enabling others within the institution to act with clarity and purpose. Emerging technologies and the changing nature of university systems. Emerging technologies are progressively influencing how universities operate, compete, and create value. The integration of artificial intelligence, AI agents, and quantum technologies is beginning to affect decision-making processes, administrative systems, research methodologies, and teaching models. Rather than focusing on technical implementation, the vice chancellor may be seen as playing a crucial role in interpreting these developments at a strategic level. This includes understanding how such technologies might influence institutional priorities, governance frameworks, and long-term sustainability. Artificial intelligence is already influencing student engagement, data-driven decision-making, and operational efficiency. AI agents appear to extend this influence by introducing more autonomous and adaptive systems across organizational processes. Quantum technologies, while still evolving, seem to signal a longer-term shift in computational capability and research competitiveness, as seen in initiatives associated with organizations such as IBM Quantum. These developments suggest that universities may increasingly operate as digitally integrated ecosystems. The vice chancellor's leadership in recognizing these patterns and aligning them with institutional strategy may become a defining factor in future success. New roles and responsibilities for senior university leadership. As technologies evolve, the roles of senior executives across universities around the world appear to be expanding in both scope and complexity. The vice chancellor may increasingly act as a coordinator of specialized leadership functions, ensuring that technological developments are appropriately interpreted and embedded across the institution. In this context, it may be valuable to consider how responsibilities could be distributed across senior leadership roles. The Deputy Vice Chancellor, Research and Impact, may engage with the implications of AI, quantum technologies, and advanced computational methods for research innovation, funding opportunities, and global collaboration. The Deputy Vice Chancellor, Teaching and Learning, may focus on the evolving nature of curriculum, pedagogy, and student experience in a technology-rich environment. The Deputy Vice Chancellor, Enterprise, Technology, or Innovation may explore institutional partnerships, digital transformation strategies, and technology-enabled revenue models. The Vice Chancellor's role, therefore, may increasingly involve aligning these perspectives, ensuring coherence across divisions, and fostering a shared understanding of technological opportunities and challenges. Leadership in a technology-driven transformation. The emergence of advanced technologies appears to call for a form of leadership that is both visionary and integrative. The Vice Chancellor may not need to engage in technical detail, but there seems to be growing importance in maintaining a clear awareness of technological trends and their broader implications. This leadership may involve framing a compelling institutional vision that reflects the opportunities presented by emerging technologies, encouraging a culture of curiosity, innovation, and adaptability, supporting informed and evidence-based decision-making across the executive team. Such an approach may help ensure that technological developments are not viewed in isolation but are integrated into the broader mission of the university. Awareness, engagement, and institutional readiness. An important dimension of leadership in this context may be the ability to foster awareness and engagement across the university community. Emerging technologies can be complex and rapidly evolving, and their implications may not always be immediately clear to all stakeholders. The Vice Chancellor may therefore consider facilitating institutional conversations about the impact of AI, quantum technologies, and digital systems, strategic forums, seminars, and workshops that bring together academic and professional staff, opportunities for cross-disciplinary collaboration and knowledge exchange. By encouraging awareness and dialogue, the Vice Chancellor may help build institutional readiness, ensuring that staff and students are better positioned to respond to change. Delegation and distributed leadership across the university. Given the scale and complexity of technological transformation, it appears neither feasible nor desirable for all responsibilities to be centralized. Instead, effective leadership may involve thoughtful delegation and the creation of distributed leadership structures. The Vice Chancellor may consider enabling different divisions to take ownership of specific areas of technological development. Research divisions may explore advanced computational methods, AI-driven discovery, and quantum research initiatives. Teaching and learning divisions may lead curriculum redesign and pedagogical innovation. Enterprise and technology divisions may focus on digital infrastructure, partnerships, and commercialization opportunities. In this way, the Vice Chancellor's role may be seen as orchestrating a coordinated institutional response, ensuring alignment while allowing flexibility and innovation within each domain. Academic planning and curriculum development. In a new era, emerging technologies are increasingly influencing the knowledge and skills required for future graduates. This suggests that curriculum development may need to evolve in response to these changes. The Vice Chancellor, as an academic leader, may play an important role in encouraging a shift towards the integration of artificial intelligence, AI agents, and quantum computing into academic programs, the development of competencies in agentic programming and digital systems, interdisciplinary approaches that connect technology with real-world applications. Such developments may help prepare students for emerging industry and research environments, enhancing employability and institutional relevance. Strategic positioning and global engagement. Universities that are able to align their strategies with emerging technological trends may find opportunities to strengthen their global position. For institutions such as Victoria University, this could involve positioning themselves as leaders in innovation, technology adoption, and interdisciplinary research. This positioning may be supported through strategic partnerships with industry and global institutions, participation in international research initiatives, development of innovation ecosystems that connect academia, industry, and government. The Vice Chancellor's role in articulating and promoting this vision may contribute to enhanced reputation, increased enrollment, and expanded funding opportunities. Communication and vision in a changing landscape. In communicating these developments, a highly inspiring and forward-looking tone may be particularly effective. The Vice-Chancellor's voice may help frame emerging technologies not as challenges, but as opportunities for growth, innovation, and impact. This communication may be conveyed through YouTube presentations and public lectures, LinkedIn posts and professional engagement, strategic discussions with senior leadership and governing bodies. By emphasizing the potential benefits, such as increased student enrollment, new revenue streams, enhanced research impact, and global recognition, the Vice-Chancellor may help build confidence and momentum across the institution. Concluding reflections. The evolution of emerging technologies appears to be reshaping the landscape of higher education in profound ways. In this environment, the Vice-Chancellor's role may increasingly be characterized by strategic insight, integrative leadership, and the ability to guide institutional transformation. By fostering awareness, enabling distributed leadership, and aligning academic and strategic priorities with global technological trends, Vice-Chancellors may position their universities for sustained success in a rapidly changing world. The opportunity is significant. With thoughtful leadership and a clear vision, universities such as Victoria University may continue to enhance their contribution to education, research, and society, while embracing the possibilities presented by emerging technologies. Professor Dr. Sardar Mn Islam, NAS may be contacted for collaboration, comments, questions, research and applications, publications, and workshops in this area via his email address, sardar.islam@vu.edu.au.
This YouTube presentation offers an analysis of the most crucial emerging technologies and explores their implications for the roles of vice-chancellors as strategic leaders in the evolving landscape of higher education. The strategic benefits of emerging technologies for Victoria University. For a university such as Victoria University, the emergence of advanced technologies appears to offer a profound set of opportunities across all core performance indicators. When viewed from a strategic leadership perspective, these technologies may contribute to strengthening the university's position in multiple dimensions. In the area of student enrollments, the integration of artificial intelligence, immersive digital systems, and advanced learning platforms may enhance the attractiveness of academic programs. Technology-enabled, future-oriented curricula often appeal strongly to both domestic and international students, particularly in high-demand areas such as AI, data science, and quantum technologies. This may support sustained growth in enrollments and diversification of the student base. In terms of external research income, emerging technologies open pathways to competitive grants, industry-funded projects, and international collaborations. Research in AI agents, quantum computing, and digital systems aligns closely with national and global funding priorities. This alignment may increase success rates in securing major grants and partnerships. Academic reputation and global ranking may also be positively influenced. Universities that demonstrate leadership in emerging technologies often gain recognition through high-impact publications, international collaborations, and participation in global research initiatives. This may contribute to improved ranking metrics and broader academic visibility. Financial solvency and revenue growth appear to be closely linked with these developments. Increased enrollments, expanded research funding, and new technology-driven programs may collectively strengthen revenue streams. At the same time, the strategic use of technologies such as AI may improve operational efficiency, contributing to more sustainable financial management. In research outputs and publications, emerging technologies provide new methodologies, tools, and interdisciplinary opportunities. This may lead to higher publication volumes, improved quality, and increased citation impact. Similarly, the availability of advanced research areas may attract high-quality PhD students, strengthening the university's research ecosystem and long-term academic capacity. These potential benefits suggest that emerging technologies are not only operational tools but strategic enablers that may influence the overall trajectory of the university. IT and engineering technologies that have implications for Victoria University. A wide range of advanced IT and engineering technologies are increasingly shaping university education, governance, operations, finance, and management, including artificial intelligence, AI, and machine learning for predictive analytics and decision-making, AI agents and agentic AI systems for autonomous workflows and institutional optimization, quantum computing and quantum information technologies for advanced research and future computational capabilities, data science, big data, analytics, and business intelligence platforms for evidence-based governance and strategic planning, cloud computing and edge computing infrastructures for scalable and cost-efficient operations, cybersecurity and post-quantum cryptography for risk management and data protection, Internet of Things, IoT, and smart campus systems for real-time infrastructure monitoring and energy optimization, digital twins for simulation, planning, and asset management, robotics and intelligent automation for laboratories, logistics, and service delivery, metaverse, virtual reality, VR, and augmented reality, AR, for immersive education and global engagement, high-performance computing, HPC, for scientific research and complex simulations, blockchain technologies for secure credentialing and governance transparency, enterprise systems such as ERP and CRM platforms for financial and administrative integration, 5G, 6G communication technologies for high-speed connectivity and digital learning environments, and advanced software engineering paradigms including agentic programming, API-driven architectures, and cyber-physical systems that collectively underpin the transformation of modern universities into intelligent, data-driven, and globally competitive institutions. Emerging technologies and the transformation of university systems. The development of artificial intelligence, AI agents, quantum technologies, robotics, and advanced digital platforms appears to be reshaping education systems and university management globally. These technologies are influencing how decisions are made, how teaching is delivered, how research is conducted, and how institutions engage with external stakeholders. From a leadership perspective, the Vice-Chancellor may be increasingly required to interpret these developments and consider how they align with institutional strategy. Rather than focusing on technical implementation, the emphasis may be on understanding systemic implications and guiding the university's response. Artificial intelligence is already contributing to data-informed decision-making, personalized learning, and operational optimization. AI agents seem to extend these capabilities by enabling more autonomous and adaptive processes. Quantum technologies, while still developing, suggest longer-term shifts in research capability and computational power, as reflected in initiatives associated with IBM Quantum. These developments indicate that universities may be transitioning towards more integrated and technology-enabled systems, requiring strategic alignment at the highest level of leadership. The evolving role of the Vice-Chancellor as a strategic leader. The Vice-Chancellor's role appears to be evolving in response to these changes. There may be increasing importance placed on strategic interpretation, institutional alignment, and long-term vision. The Vice-Chancellor may act as a central figure in connecting technological developments with academic priorities, financial planning, and global positioning. This role may involve recognizing emerging trends, assessing their relevance, and facilitating informed discussions within the executive team. It may also involve ensuring that the university remains responsive to external developments while maintaining its core mission and values. New responsibilities across senior executive leadership. The expansion of technological influence across university systems suggests that responsibilities may be distributed across senior leadership roles. The Vice-Chancellor may play a coordinating role, ensuring that each division engages effectively with relevant developments. The Deputy Vice-Chancellor, Research and Impact, may explore opportunities in AI-driven research, quantum technologies, and interdisciplinary innovation. The Deputy Vice-Chancellor, Teaching and Learning, may consider how curricula and pedagogical approaches evolve in response to emerging technologies. The Deputy Vice-Chancellor responsible for enterprise or technology may engage with digital transformation, partnerships, and innovation ecosystems. Through this distributed leadership model, the Vice Chancellor may ensure that technological awareness and strategic alignment are embedded across the institution. Academic planning and curriculum development. Emerging technologies appear to be influencing the knowledge and skills required for future graduates. This suggests that curriculum development may need to reflect these changes in a systematic way. The Vice Chancellor, as an academic leader, may encourage the integration of artificial intelligence, AI agents, quantum computing, and digital systems into academic programs. The concept of agentic programming, where systems operate with a degree of autonomy, may become increasingly relevant across disciplines. Aligning teaching, research, and innovation with global technological trends may enhance the relevance and competitiveness of academic offerings. This alignment may also support stronger engagement with industry and research partners. Strategic positioning and global engagement. Emerging technologies appear to provide opportunities for universities to strengthen their global position. By demonstrating leadership in areas such as AI, quantum technologies, and digital innovation, institutions may enhance their reputation and attract international collaborations. For Victoria University, this may involve positioning itself as a hub for emerging technologies, fostering partnerships with industry, and participating in global research initiatives. Such positioning may contribute to increased visibility, improved rankings, and expanded opportunities for students and staff. Awareness, engagement, and institutional culture. An important aspect of leadership in this context may be fostering awareness and engagement across the university community. Emerging technologies can be complex, and their implications may not always be immediately clear. The Vice Chancellor may consider supporting initiatives that promote understanding, such as seminars, workshops, and interdisciplinary forums. Encouraging dialogue and collaboration may help build a culture that is open to innovation and responsive to change. Delegation and coordinated institutional response. Given the scale of transformation, it may be appropriate for responsibilities to be distributed across different divisions of the university. The Vice Chancellor may facilitate this process by enabling each division to engage with relevant technological developments. Research divisions may focus on advanced computational and scientific innovation. Teaching divisions may lead curriculum redesign and pedagogical development. Enterprise and technology divisions may address infrastructure, partnerships, and digital strategy. This coordinated approach may help ensure that technological developments are addressed comprehensively while maintaining alignment with institutional objectives. Communication and vision. Communicating the implications of emerging technologies may be a central element of the Vice Chancellor's role. A clear, inspiring, and forward-looking message may help build confidence and shared purpose across the institution. Such communication may highlight the potential benefits of technology adoption, including increased enrollments, enhanced research capacity, improved financial sustainability, and strengthened global reputation. It may also emphasize the university's commitment to innovation and its role in shaping the future of education. This approach may be particularly effective across platforms such as YouTube, LinkedIn, and executive presentations, where strategic messaging can reach diverse audiences. Concluding perspective: the emergence of advanced technologies appears to be reshaping higher education in significant ways. For Vice Chancellors, this may represent an opportunity to guide their institutions through a period of transformation, aligning technological developments with academic and strategic priorities. By focusing on awareness, coordination, and vision, Vice Chancellors may help position their universities for sustained success. For Victoria University, this may involve leveraging emerging technologies to enhance enrollments, research income, reputation, and overall institutional impact. The future of higher education may increasingly depend on how effectively these opportunities are recognized and integrated into a coherent and forward-looking strategy. Contact: Professor Dr. Sardar M.N. Islam, NAS, at Victoria University, may be contacted for collaboration, comments, questions, research and applications, publications, and workshops in this area via his email address, sardar.islam@vu.edu.au